Right, everybody. Let's continue with Introduction to Simulation Program Series 2. Well, for the lab, uh, not only that you are going to learn how to use LTspice and also be familiar with LTspice. You also we work on some circuits, and this in this case is going to be about our Thevenin equivalent circuit. Let's start with the objectives. Well, for the lab, one is to be familiar with LTspice. Number two, you should be able to draw circuits, different type of circuits, and apply electronic components. And number three, be able to simulate the work to analyze DC circuits. And the last one is be able to analyze DC circuits for various DC power supplies. Um, let's take a look. For the simple one, as I mentioned earlier on the YouTube series 1, you have only one supply voltage in series with resistor R1 and also in series with the resistor R2. Each one is 10K and 1K and 10K for R2. By Ohm's law, you know V equal to IR, where V is the supply voltage or the voltage. I is the current in the unit of ampere, and R is the resistance in the unit of ohms. And you can find the current flowing through the circuit. In this case, the current flowing through R1 and R2 is going to be the same because they are connected in series. And you have a supply voltage 5 volts, and you are the total resistance going to be 1K plus 10K. That's end up with 0.45 milliamp. And you also know that the voltage drop across R1 equal to IR1, where the current is 0.45 milliamp and your R1 is 1K. So let's give you 0.45 volt. That means for the supply voltage 5 volt, some of them will drop across resistor R1. So that's why you have less voltage than 5 volt. And you know the voltage drop across R1, that's the equal to the difference between the voltage between A and B, the nodes. And VA minus VB equal to what? 0.45 volt. And you can find your VB, simply VB equal to VA minus 0.45 volt. That's the 4.55 volts. The voltage drop across the R1. And let's see if I do something wrong. Oh, this one is okay. Milli and kilo, let's give you milli is 10 to a negative third, and K is 10 to the cube. So let's give you 1. So you end up with 0.454. And again, this is the summarization to use LTspice to rotate your devices. Simply you do a Control R, and if you hit F3 on your keyboard, that's you do wiring between two components. Delete, like hotkey F5, duplicate hotkey F6, move F7, drag F8, and ground, that's the G. Also, the mode of analysis. You go to main menu, edit, and then you go to submenu, LTspice analysis. You have a transients mode. That means you want to plot uh, respect to time. AC analysis, you want to plot respect to frequency. DC sweep, you want to plot respect to the voltage. And DC operating point, you analyze each node for current and voltage. Now the lab procedures. The first one, they ask you to take the record of V1, V2, V3, IR1, IR2, IR3, IRL, which is load, and IV1, that's the current flowing through the supply voltage. And for R1, students have different value of R1. You applied your last 3 digits number of your student ID. So I label the node as reference V1, V2, V3. Let's go to your circuit down here. That's the node 1, node number 2, node number 3. And you have R3, 150 ohms, R2, 200 ohms, and RL simply is load, which can be a motor or a light bulb. And what you need to do is you draw the circuit, and then you take a record for V1, V2, V3, and you also have IRL, and we move to Thevenin equivalent circuit later on. That's the part number 1 of your lab. Number 2, now we move to Thevenin's theorem, where we're basically, or in principle, you can see that when you have the load in the term of motor or any type of external devices, you connect to your supply voltage with include 3 resistor or R1, R2, and R3. So to make the circuit simple, you want to simplify the circuit by only have one supply voltage and one supply resistor. I mean, in the supply voltage. So you need to follow this step. At this point, you want to simplify the circuit to have only VTH and RTH. That's for the supply block, and you connect it to your load resistor or motor or light bulbs, etc. V1 not equal to VTH. RTH is depends upon R1, R2, and R3. So we're going to work this out. How can we find VTH and RTH? Okay, let's get back to the step number 2. VTH, that's the Thevenin's voltage, and RTH is the Thevenin's resistance. Let's start with the VTH first. VTH simply V open. What does this mean, V open? It means that you remove your load resistance, resistor, or you remove your motor, you remove your light bulb. And what you're looking for is a V open. Now take a look at the node number 2 and number 3. Since this is an open circuit, it's not a complete circuit, so you have no current flowing from you have no current flowing through resistor R3, and that's mean your voltage at the node number 2 is equal to the voltage at the node number 3, because delta V equal to IR by Ohm's law. when I equal to 0. That means delta V equal to 0, or delta V equal to V2 minus V3. So you end up with V2 equal to V3, correct? Now, this one is easy to do calculation for V2 or V3. But now we're going to use the LTspice to analyze the circuit. We're looking for V open or V3 or V2. So what you can do, you remove your external device, and then this is what you have left over. You can do this by calculate by hand if you want to do if you look for the voltage at the node number 2, which is the V open. That's the same as the V at the node number 3. So this one simply, you can do the voltage divider, right? You have the source voltage V1, and you do the voltage divider. So your V open, that's going to be V1 multiplied by R2 divided by R1 plus R2. You know about that before. Okay, so that's for V open. Now for the LTspice, you need to apply the DC transfer mode. And what you need to put in is that you're looking for V3. And actually, this one is for output resistance. You already know that V open from LTspice. So you need to put the command .tf, that stands for transfer function. V3, that's what you're looking for, and the source voltage is V1. And it will give you the output resistance for various supply voltage, V1, 75, 90, and 120. Okay, so you already have all data to record in the table number 2 for V open and output resistance in the unit of ohms. Now for step number 3, Thevenin equivalent circuit. What you need to do is that you need to represent the whole circuit here to be your Thevenin equivalent circuit. That means you have only one supply voltage, VTH, and you have only one internal resistance, RTH. That's connected in series with RL. For Thevenin theorem, this means that UVTH is going to be equal to V open or V2 or V3 because both of them are equal. So when you remove your load resistor, you end up your circuit like this with no supply voltage. And you can calculate for a total, the input resistance. That's become RTH. From the resistor network here, R1 in parallel with R2, and then in series with R3. So your R total is going to be R1 in parallel with R2 plus R3. Straightforward. That's equal to RTH. For example, in the circuit, you have R1 equal to 200 ohms, and R2 is 200 ohms. R3 is 150 ohms. So your R total become 250 ohms. Take a look at this quick. When the same resistance are in parallel, this will drop to the half of that resistance. So 200 in parallel with 200 is dropped to 1/2 of 200 ohms. So that's give you 100 ohms. And then you in series with R3. 150 ohms, that's the 250 ohms. That's your RTH. So you already have VTH and RTH. Okay. And now take a look at V1. As I mentioned earlier, since you remove your load resistor, you end up with the circuit like this. Your VTH is simply become the voltage divider of V1. So VTH equal to V1 multiplied by R2 divided by R2 plus R1. In this case, the V1 equal to 75 volt, R1 200 ohms, R2 200 ohms, and R3 150 ohms. So your TH, that's going to be 75 multiplied by 200 divided by 200 plus 200. And you end up with the VTH equal to 37.5 volt. So in conclusion, for the Thevenin equivalent circuit, you have VTH to be 37.5 volt, and your RTH is the 250 ohms. Okay, and you will verify both circuit later on. If you do the equivalent circuit, uh, you need to make sure that you do it right by verify that the current flowing through RL from the first circuit equal to the current flowing through RL in the second circuit. Okay, and if you do the circuit on the LTspice later. Now you can do a hand calculation. The other ways that are from Thevenin theory, your what you're looking for equivalent Thevenin circuit is that you're looking for VTH and R short, and you need to prove that it's equal to R total from the previous step. This one, R total equal to R1 in pair with R2 plus the R3. Okay, let's start. Well, your I short is that means you short your R circuit, so you have no load, or the load resist stands become what? Zero, right? Because you short circuit. And then you can find I short by calculation. That simply become you do the R total first. Your R total simply become R3 in parallel with R2 and in series with R1, right? And the current flowing through R1, that's going to be equal V over R by Ohm's law. So that's V1 divided by R3 in parallel with R2 plus R1, that's in series. And now you're looking for R3, that's the I short. You need to do the current divider. That's different than the voltage divider. Because you want to calculate for the current flowing to R3, you need to do the current divider. So this is your current flowing through R1, and you need to divide it, divide your current into R3 and R2, or AR3 plus AR2, the outgoing current. That's going to be equal to incoming current, or IR1. That's the KCL, right? Kirchhoff current law. And for the voltage divider, you need to multiply by R2, not R3. You already know about it. You study physics, electrical circuit uh, when you was a freshman, the first year student. And then you want to write V1 in the term of VTH. That's what we're looking for. VTH, that's the voltage divider. V1 multiplied by R2 divided by R1 plus R2. Let's get back to the previous step for VTH. Where do I have VTH? Yep, this one, your VTH. That's the voltage divider. VTH equal to V1 multiplied by R2 divided by R1 plus R2. And then you can write V1 in the term of VTH, simply equal to VTH multiplied by R1 plus R2 divided by R2. So you just plug in. This is your V. What's that? This has become your. All right, hold on a second. Okay, V1 equal to R1 plus R2. So you have this. This is your V1, the whole term here. Divided by R2 VTH, that's V1, and you still divided by R3 in parallel with R2 in series with R1. So R3 in parallel with R2 equal to R2 R3 divided by R2 plus R3. And you still have this term. R2 cancel out. Okay. Now you need to expand, this term. Rearrange, the whole term. So you have R1 plus R2, and then you still have VTH divided by R2 plus R3, and then plus R1 multiplied by R2. That's common denominator, sorry, common denominator. And then finally you have R2 plus R3 cancel out. So your I short equal to VTH multiplied by R1 plus R2, and this is the R1, R2 plus R1, R3, and then R2, R3. Okay, and this one, you take a look at this. You take the common term out. This one, R1 plus R2. This one cancel out. So you have R1, R2 divided by R1 plus R2, right? And then plus R3. So it's the same as your R total that you did calculation before this one. So in conclusion, the other way to do the calculation for RTH and VTH, especially for RTH, you simply look for VTH or V open divided by I short, which is the current flowing through R3. Okay, that's in practical. You measure your VTH and you measure your I short. Thus, you end up with your RTH. Let's summarize. That's mean for Thevenin equivalent circuit, you look for VTH and RTH. Your VTH simply become V open. You remove your external device, and then you do the measurement of the voltage at this point and this point, which are the same. And for your I short, that's equal to the current flowing through R3. Okay, and then when you have both V open and I short, you divide V open by I short. Sorry, I'm missing here, and that will give you RTH. That's the Thevenin equivalent circuit. Okay, now let's go to sorry, LTspice. I already have the circuit right here. So you start with the complete circuit. You have R1, you have R2, R3, and this is your load resistance. And you have the supply voltage, 75 volt. And this one, for step number 2, you're looking for the output resistance. So the command that you're looking for is that I'll start over again. So I remove this one, and you go to edit. You go to LTspice analysis, and you do DC transfer. So when you're looking for output resistance, you need to put your output actually. That's you look for the open circuit. So you need to remove RL. So I just uh, delete this one. Okay. And then now you go to the analysis mode. It is transfer. Your output become V and then C. Okay. And then your source simply V1. Click OK. And you have this is transfer function VC and V1. Let's give you your output impedance, which is the 250 as we calculated before. Okay. And for the recording of your data, let's see, where is the, okay. For step number 2, you need to do a recording for your output resistance for various supply voltage, 75, 90, and 120. So from your circuit, you simply change, by right click on the supply voltage to change this one to be what? What I have 120. Okay. And then you do simulation again. This will give you your output impedance to be 250 ohms. All right. So that step number 2 of your lab. And for number 3, Thevenin equivalent circuit. Let's focus on the supply voltage 75 volt. You know that your VTH equal to 37.54 and your RTH is the 250 ohms. Let's see. I do have Thevenin equivalent circuit. Oops, not this one, sorry. Okay, let's start over again. At the beginning, I have Thevenin here. Okay, doesn't matter. The complete circuit. I also have for the load resistance, right? Put this one, and you right click on R4 and put that's the load RL, and that you click on R, right click, and you enter the new value. That's the what 200 ohms, right? For your resistance of your load. Okay, as I mentioned earlier, for Thevenin equivalent circuit, your current flowing through RL have to be the same. This is your original circuit. And now if I want to do Thevenin equivalent circuit, I simply I copy this one. So you go to edit, you go to duplicate, and then you copy all your components that you're looking for, right? Left click, you place, right click to stop. Got to be careful here. You cannot have the same node label. So I change this one to be D, right? We already have C, and this become E. Well, the reason I'm doing these two circuits is because I want to compare the original circuit and Thevenin equivalent circuit. The current flowing through RL from both circuits have to be the same, otherwise you did something wrong. And then you don't need this one because you're not looking for output resistance. I'm going to kill this. You go to scissor, you kill it, you kill it. And then what else I need to change? This RL, let's put this one become RL1. And this also become RL2. RL2. And this is not, okay, let's do this as the 75. That's the start supply voltage. And this one is not, we want not, this one you want to be VTH, right? RTH. Okay. And this one not equal to 75, but by doing LTspice or calculation, this one end up to be what? The half of 75. So that's the 37.5, right? Okay. And this is your RTH. And from LTspice and calculation, this one is what? 250, right? Ohms. Okay. Now what we're looking for is that this is the original circuit. And this one is Thevenin equivalent circuit. You have only one supply voltage and you have only one resistance or resistor. That means if you do it right, the current flowing through the load from both circuits have to be the same. All right, keep your eye on this. Now you do simulation, you go run, and then you do DC operating point. Click OK. Now take a look at this. The current flowing through RL1 is what? IRL1, this guy. 0.029. Oops, sorry. L1, this one. That's 0.0833. And the current flowing through the load from our Thevenin equivalent circuit, RL2, that also is the same because this one is what? 0.0833. So you did it right. And that's the conclusion of how you work on a Thevenin equivalent circuit. The main point is that you need to look for VTH and RTH. Okay, so that's all for now for introduction to LTspice. And this one is concerning Thevenin equivalent circuit or Thevenin theorem. Okay.